So imagine for a second that you're paying this massive team of master architects to design, I don't know, $1 million skyscraper.
Okay, yeah, a massive investment right off the bat.
Right. And they draft all the blueprints, they pour the foundation, they build it flawlessly over, like, months of painstaking labor.
Sounds like standard construction so far.
Exactly. But then, the very moment you walk out the front door, they just wire the entire building with explosives and completely blow it to dust.
I mean, that sounds like complete madness. You've just destroyed the entire asset.
It totally does. But, well, what if I told you that is exactly what the future of software engineering actually looks like?
Oh, wow.
Yeah. So welcome to the Deep Dive. If you're joining us today, and we always love having you, the learner, with us, we have a very specific mission.
We really do.
We are unpacking this highly provocative, state-of-the-art research paper. It's featured in Architecting Intelligence, the Jane AI Research Chronicles.
Right, published recently.
Yeah, in June 2026 by Zhenfeng Cao. And the title alone is just a massive shot across the bow of the whole tech industry. It's literally called The End of Software Engineering.
And we should definitely clarify up front that title is not just some, academic clickbait.
Not at all.
The author is arguing for a total fundamental restructuring of how software is actually created. I mean, it is a complete teardown of a 50-year-old paradigm.
Okay, let's unpack this. Because this isn't just about, like, a new autocomplete tool for developers.
No, it's way bigger than that.
Right. If you are a seasoned coder, or even if you're just someone trying to navigate your career in a tech-driven world, this shift directly affects you.
Absolutely.
The core premise we are exploring today is that AI agents are turning code from this permanent, carefully crafted product into, well, a totally disposable temporary tool.
Which is wild to think about. But to really understand why a massive industry is suddenly embracing disposable code, we actually have to look backward before we look forward.
Oh, definitely.
We have to examine the foundational flaw that software engineering was actually built upon. And it all traces back to a very specific crisis in 1968.
Right, the 1968 NATO Software Engineering Conference. I remember reading about this. This is literally where the term software engineering was coined, right?
Yes, exactly. Yeah. And it was coined out of sheer panic, honestly.
Wait, actual panic?
Total panic, yeah. In the late 60s, hardware was advancing incredibly fast. Computers were getting exponentially more powerful every year.
Because of Moore's Law, basically.
Exactly. So because of that, companies and governments started attempting to build these software systems that were vastly larger than anything they'd ever tried before.
And I'm guessing that didn't go well.
It was a disaster. The systems were just collapsing under their own weight. Ad hoc programming, just having a really smart guy sitting in a room typing logic. It just couldn't manage the massive complexity.
Wow.
Yeah, projects were years late, vastly over budget, and just full of critical bugs.
So the industry had to introduce rigorous methodologies to compensate for that, right? They brought in, like, structured design, systematic testing, modular decomposition.
Right.
All the stuff that makes software development look like traditional, physical engineering.
Right. They basically applied a physical manufacturing mindset to a digital problem.
Makes sense.
And for 5 decades, it was the best we had. We went from waterfall methodologies to agile sprints, from these massive monolithic applications to microservices.
But the Cao paper points out that the deepest, most structural problem of that 1968 crisis never actually went away, did it?
No, it didn't. The paper actually leans heavily on Fred Brooks's classic book, The Mythical Man-Month. Specifically, his distinction between 2 types of complexity.
Accidental and essential complexity, right?
Exactly. So accidental complexity is the stuff we can actually fix. It's the friction of, bad tools, slow compilers, or clunky programming languages.
Right. And we've spent 50 years basically fixing that accidental stuff.
We have. But essential complexity is totally different. Essential complexity is the inherent, unavoidable difficulty of the problem you're actually trying to solve.
So it's baked into the task itself.
Yes. Unlike building a physical bridge, where there is a distinct design phase and then a manufacturing phase, well, in software, the design is the product.
Oh, that's a really good point. Every single line of code is a design decision.
Precisely. And the paper actually lays out the formal math on this essential complexity, and it is pretty sobering.
Let's hear it.
If you have a system with n components, the number of possible interaction paths between those components grows combinatorially. It's mathematically bounded by 2 to the power of n.
2 to the power of n. Okay, let's make that concrete for a second.
Yeah.
Think of traditional coding kind of like hosting a dinner party.
Okay, I like this.
If you have 2 guests, You basically just need to know if they get along. One single interaction to manage.
Right, super easy.
But if you invite 10 guests, you aren't just managing 10 people. You're managing the 1,024 different potential arguments, alliances, inside jokes, and food allergies between every possible combination of those guests.
That is a lot to keep track of.
Exactly. And if you have a software system with thousands of components, that math explodes exponentially into the billions.
That's staggering.
Traditional software engineering is like trying to build a city out of glass blocks. Every new block you add increases the chance that a vibration on one side shatters the other.
That's a perfect analogy.
The human brain simply cannot track all those vibrations. It physically cannot hold all those interactions in working memory.
And that fixed cognitive limit of the human brain is the crux of the entire issue. Humans have a hard biological cap on systemic understanding.
Right.
But we've been stubbornly trying to solve an exponentially growing complexity problem using that fixed capacity brain.
Which perfectly explains Brooks's law, doesn't it?
Yeah.
The famous observation that adding a new developer to a late software project only makes it later.
Exactly, because you're just adding more guests to the dinner party. The communication overhead and the risk of breaking some unseen connection just gets way too high.
Okay, so that brings us to the core thesis of the paper.
It does. The end of traditional software engineering isn't happening just because AI is some trendy new tool.
Right, it's not a fad.
No, it's an inevitable mathematical consequence. We have simply reached the ceiling of what human working memory can manage.
Wow.
We literally cannot continue to explicitly encode every single logic decision into static text using human brains. It doesn't scale.
Wait, but if we can't solve this O2 to the N complexity with human brains, how do we build software going forward?
That's the big question.
Do we just accept that massive applications will always eventually crash? Or just grind to a halt?
We don't accept it. We just stop making humans own the complexity. We shift the burden entirely.
Okay, how so?
The paper traces this evolution through 3 distinct generations of software delivery, and it leads directly to the death of the code artifact itself.
All right, let's walk through those. Generation 1 would be software 1.0. This is the era of local software and licenses.
Yeah, think of buying a CD-ROM in the 90s and installing it on your desktop computer.
Right, I remember those days.
Yeah.
In this model, the end user basically owns almost all the complexity.
Exactly. You have to maintain it, run the manual updates, worry about whether your computer's hardware is even compatible.
Yeah, it was a headache. So then the industry moved to software 2.0, which we all know as SaaS, where software is a service.
Right. And here, the vendor absorbs the infrastructure complexity.
So the code and the database, they execute on some distant cloud server somewhere.
Yep. And the user just logs in through a web browser and pays a monthly subscription.
Which was a massive liberation. I mean, it meant a small business didn't need to hire a whole IT team just to run a noisy, overheated server room down the hall.
Exactly. It abstracted the hardware away. And now, the Cow paper introduces software 3.0, which is AT Agent as a service.
Agent as a service.
Yep.
Okay.
In this new model, an autonomous agent operates in the cloud. It absorbs the complexity of understanding the problem, writing the solution, executing it, and then delivering the result.
But to truly understand AIs, we have to look at why our current attempts to use AI in coding are kind of failing to solve that essential complexity we just talked about.
That's a crucial point. You mean the current dynamic where a developer basically just uses a copilot tool to write code faster?
Yeah, the paper calls this the AI to software to result pipeline.
Right. That pipeline has massive structural weaknesses. First off, the human is actually still the bottleneck.
How so?
Well, the AI might type the boilerplate code at light speed, sure, but the human developer still has to read it, integrate it, test it, and deploy it.
Ah, I see.
Second, the final product is still a traditional static software system. It's still that dinner party with a billion possible interactions.
So its complexity is still strictly bounded by what a human brain can understand, and they inevitably have to go in and modify it later.
Exactly. So we're really just building the impossibly complex system faster, which means we're going to hit the ceiling of human comprehension even quicker.
Which is exactly why the paper argues we have to move to an agent-to-result paradigm.
Yes, cut out the middleman entirely.
In this model, the human articulates an intent. The agent plans a strategy, generates the necessary code, executes it, gets the desired result for the user, and then, and this is the crazy part, it immediately deletes the code.
It just throws it away.
Okay, I have to push back here, wait.
Go ahead.
If the code is ephemeral and just gets thrown away the second the task is done, What is the customer actually paying for?
That is the million-dollar question.
Are we saying the software artifact itself, like the app, the script, the code base that a company traditionally values as intellectual property, is just dead weight?
If we connect this to the bigger picture, it actually makes perfect economic sense. We are moving to a purely outcome-based model.
Okay, explain that.
Think about using a calculator. When you type in a really complex equation, do you care about the intermediate binary mathematical steps the microchip takes to solve it?
No, of course not. I just care about the final number on the little LCD screen.
Exactly. The intermediate steps are totally irrelevant to you. In AAS, the code is just the agent's internal thought process. It's literally just scratchpad math.
Oh, wow. That's a crazy way to think about it.
Just like SaaS liberated us from managing server hardware, it liberates us from having to care about how a digital result is actually produced.
So the artifact is meaningless, the outcome is everything.
Exactly.
So if I'm not writing the code, and the code is just a transient thought process in a machine, what exactly is happening under the hood? Like, how does this agent actually think and operate without a human holding its hand?
Well, the paper introduces the entirely new discipline replacing traditional software engineering. It's called Agentic Engineering.
Agentic Engineering.
Right. A concept formally framed around April 2026 by LangChain. It's basically defined as multi-agent coordination, where AI acts as autonomous digital team members.
And there is a very specific framework for how they operate, right? Primarily based on perception, memory, action, and an LLM reasoning core.
Yes, those 4 pillars. Let's break those down. What does perception actually mean for an agent?
Yeah, it doesn't have eyes.
Right, but it means multimodal input. The agent isn't just reading a text prompt anymore. It can essentially see the user interface of an app.
Oh, like taking screenshots and analyzing them.
Exactly. It can read system error logs in real time, monitor network traffic, all of it.
Wow.
And then there's the action layer. This isn't just outputting a paragraph of text. Action is the agent's ability to actually use external tools.
Like what?
Like autonomously querying a live database or spinning up a virtual machine on AWS to test something.
But the real magic, to me at least, seems to lie in the memory architecture.
Oh, absolutely. The paper divides this into semantic, episodic, and procedural memory.
Right. And there's a real-world example in the sources that illustrates this beautifully. The Hermes agent by Noose Research.
Hermes is fascinating.
And this thing isn't just theoretical, right? It has like 179,000 stars on GitHub.
It does. Hermes is a phenomenal case study in agentic engineering. It features what they call a closed learning loop.
Okay, how does that work?
Let's say you give Hermes a highly complex, really messy data extraction task. It doesn't just stumble through the task and then forget about it once it's done.
Like a normal ChatGPT prompt would.
Exactly. It autonomously generates a reusable skill, which the paper calls a parameterized procedural module.
Okay, let's translate that jargon for a second. A parameterized procedural module. Think of it like a chef creating a master recipe, but they leave the specific ingredients blank.
That's a great way to put it.
The agent figures out a brilliant sequence of steps to scrape data from some notoriously difficult website, and it saves that sequence as a template.
Right.
Next week, when you ask it to scrape a completely different website, it pulls out that blank recipe, plugs in the new variables, and executes it perfectly without having to relearn all the hard parts.
It literally creates its own tools.
It's insane. It creates a tool, uses it, realizes the tool is flawed, and then fixes it without a human ever clicking a mouse.
It is remarkably self-sufficient. But, what's even more crucial is how Hermes handles episodic memory.
Right, this part is wild.
It uses something called FTS5-backed conversation search, combined with LLM summarization.
Okay, FTS5 being a very fast text search extension. Why is that so critical here?
Because it allows the agent to maintain deep continuity across completely disconnected sessions.
Oh, so it doesn't just wake up with amnesia every day.
Exactly. If an agent is going to replace a human developer, it can't start with a blank slate every morning. Through this search mechanism, the agent actually remembers a weird bug it encountered on a Tuesday 3 weeks ago.
That's wild. It accumulates experiential knowledge over time.
Yes, it learns the unique, undocumented quirks of your specific business logic, exactly like a human senior engineer naturally does.
Okay, that sounds incredible. Honestly, it sounds like sci-fi magic.
Yeah.
But as with everything in the AI space, we have to separate the hype from reality.
Always. We have to look at the data.
Right. Does the empirical data actually back up this capability today?
Well, the benchmark data in the paper tells 2 very distinct stories. There are massive triumphs, and then there is a very sobering reality check.
Let's start with the triumphs because they are huge. The paper points to a model called Lingma SWE GPT-72B.
Right, Lingma.
This is an open model, and it managed to resolve 30.29% of real-world, highly complex GitHub issues on the SWE benchmark.
And to put that 30% in context, it is hovering right behind massive proprietary giants like GPT-4o, which got around 31.8%.
But what is truly staggering to me is that Lingma SWE GPT actually beat Llama 3.1 405B.
Yes.
Llama 405B is this massive, incredibly expensive model with 405 billion parameters.
Yeah.
Lingma beat it with a fraction of the compute power.
It's incredible. And how did they do it? Because Lingma wasn't just trained on millions of lines of static finished code.
What was it trained on?
It was trained on the actual process of coding. The mistakes, the debugging steps, the iterative development.
Oh, it learned how to think like a coder, not just read code.
Exactly. And then there is the multi-agent triumph.
Oh, the LangChain pilot. The sources detail this LangChain pilot program deployed across 20-plus enterprise debugging workflows.
Right. They didn't just use one smart AI. They deployed a whole swarm of agents.
And the result was a 93% reduction in the time it took to identify the root cause of bugs.
93%. That is unheard of.
Saving over 200 engineering hours in a single month.
And we really have to look at how they achieved that massive reduction. It wasn't because the individual agents were inherently smarter.
It was the orchestration.
Yes. They cross-validate each other. You assign one agent to trace the network logs. You have another comb through recent code commits. And a third agent acts purely as a devil's advocate.
Just actively trying to poke holes in the theories of the first two.
Exactly. They parallelize the investigation and debate each other in milliseconds. It is quite literally silicon-based teamwork.
Okay, here's where it gets really interesting, though.
Oh, yeah.
Because right after celebrating these massive wins, the paper drops the EvoClaw benchmark.
Uh-huh.
And, well, EvoClaw is a cliff.
EvoClaw is the necessary reality check we need.
Right. Unlike standard benchmarks that measure performance on an isolated bug fix, EvoClaw measures continuous software evolution.
Right. It tests whether an agent can actually sustain development over a long history of commits, feature additions, and changing requirements over time.
And the performance just plummets. When agents are given isolated single tasks, they hit an 82% success rate.
Which is great.
But when they are forced to do continuous evolution, that success rate drops by 54%. They fall to just a 38% success rate.
It's a brutal drop.
Wait, I have to challenge this. You're telling me an AI swarm that can out-debate human engineers and beat a massive 405 billion parameter model just randomly forgets how a code base works after a few updates?
I know, it sounds counterintuitive.
It makes no sense. If it gets confused, why wouldn't the agent just reread the code from scratch?
Because of a phenomenon called context drift.
Context drift.
Right. As a code base grows and evolves over months, the sheer volume of architectural decisions, implicit dependencies, and hidden logic exceeds the agent's effective memory window.
Oh, I see.
Rereading a million lines of code doesn't actually tell you why a specific weird workaround was put in place 3 months ago. They lose the big picture.
Okay, so it's the difference between building and maintaining.
Exactly.
AI can build a house in a day, but if you ask it to renovate the kitchen a year later, it accidentally demolishes the garage because it lost track of where the load-bearing walls are.
That is exactly the issue, and that context drift leads directly to the second major challenge.
Yeah.
Error propagation. An agent makes a tiny, mathematically logical, but contextually wrong assumption in commit number 2. By commit number 10, that error has compounded, and the whole system is completely unstable.
Because they lack technical debt awareness.
Precisely. They are optimizing to get the immediate task off their plate today, but they aren't modeling the long-term nightmare they are creating for maintenance tomorrow.
Oh. And the final hurdle is verification fidelity, right?
Yes. An agent can write code that perfectly passes an automated unit test in a little sandbox, but it still introduces a subtle semantic error that only triggers when real users interact with the system at scale.
So if you are listening to this right now and you're a mid-level Python developer, you might be sweating a little bit at that 82% success rate on single tasks.
Understandably.
But that 38% EvoClaw score proves that fully autonomous, hands-off engineering isn't taking your job today. We can't just hand the keys to an agent and go to the beach.
No, this raises an important question. We can't do it today. But the trajectory of the technology is undeniable.
Right, the gap between isolated success and continuous evolution is, at its core, fundamentally an engineering problem. Memory architectures and context windows are improving rapidly.
They really are.
Which brings us to the ultimate question. Knowing that this transition from permanent code to ephemeral agentic action is messy but inevitable, what is the timeline?
It's moving fast.
And more importantly, what do you, the listener, actually need to do to survive and thrive in this new landscape?
Well, the research outlines a very clear four-stage evolutionary roadmap.
Let's hear it.
Stage I spans from roughly 2023 to 2025. This is the tool-augmented era, the co-pilot era.
Right, where the human authors the code and the AI just acts as a smart assistant. We're sitting at the tail end of that right now.
Exactly. Then we transition into Stage 2, from 2025 to 2027. This is single-task autonomous.
This is where tools like Devin or OpenHands come in, right?
Yes. The agent actually owns a complete feature on start to finish. The human shifts from writing syntax to just specifying the intent and reviewing the final pull request.
But as we discussed with EvoClaw, single agents hit a context ceiling pretty quickly.
They do. So, to solve that, we move to Stage 3, from 2026 to 2029, multi-agent teams.
Right.
This is where systems like MetaGPT take over. We literally split the AI's brain. You have specialized agents acting as product managers, architects, and QA testers, mimicking human corporate structures to handle immense complexity.
Wow. And finally, Stage 4, 2028 and beyond, self-evolving ecosystems.
The final frontier.
This is where the agents autonomously monitor systems, discover bottlenecks, learn, adapt, and rewrite their own underlying architectures without any human intervention at all.
It's wild. The very distinction between the software and the agent just dissolves.
So navigating this roadmap requires a massive reimagining of the human role.
Absolutely. In the 1968 paradigm, your primary value as an engineer was your ability to produce correct, efficient, bug-free code.
But in the agentic paradigm, code generation is completely commoditized. It's cheap.
Exactly. So the future 10x engineer, that legendary archetype of the developer who does the work of 10 people, isn't the person who can type Python the fastest.
Right. The new 10x engineer is the best agent orchestrator.
Exactly. The paper defines 4 new human differentiators for this era.
Let's go through them.
First is intent articulation. Can you specify a business goal with such rigorous clarity and constraint that an autonomous agent won't produce an unintended catastrophic outcome?
That's a huge skill. What's second?
Second is architectural oversight. You need to understand how to design the actual communication pathways for a swarm of agents.
Right. Who talks to who?
Yeah.
Third is quality calibration. You have to find what good actually looks like.
Yes. If the agents are generating the code, you have to build the rigorous evaluation framework so the agents have a metric for self-correction.
Makes sense. And fourth is ethical governance, ensuring the agent's autonomous behavior strictly aligns with legal compliance, privacy standards, and company policy.
The actionable advice here, really, is to adopt a human-in-the-loop, agent-in-the-driver's-seat posture.
I love that phrasing.
Look at your daily workflows. Identify which repetitive debugging or deployment tasks are agent-ready right now, and start practicing your orchestration skills.
So what does this all mean? Let's pull all these threads together.
Let's do it.
The 1968 software paradigm, the era of human-encoded static logic, is coming to a close.
It really is.
That essential complexity, the O2 to the end dinner party that human brains simply can't manage, is finally being offloaded onto LLMs that can scale infinitely with compute.
Right.
Code itself is becoming ephemeral. It's no longer a permanent brick in a digital wall. It's just a temporary thought in the mind of an AI.
Beautifully put.
Your job is no longer to write the syntax. Your job is to architect the intent.
The transition to agent as a service is moving incredibly fast. I mean, the empirical evidence shows both the massive potential of multi-agent swarms and the current hurdles of context drift. But the destination is undoubtedly set.
Which leaves us with one final thought for you to mull over. We talked about the skyscraper analogy at the beginning, about building a massive structure just to tear it down.
Right.
If the ultimate trajectory of agentic engineering is that software writes, tests, and evolves itself purely based on our stated goals,
Yeah.
well, does that mean the most important programming language of the future won't be Python or Rust or C++ ammo?
Oh, I see where you're going.
Will the ultimate programming language simply be your mastery of the English language?
Wow.
Think about it. What happens to the world when everyone who can clearly articulate a deeply complex idea instantly becomes a master developer?
It's a profound equalization, really. The technical barrier to digital creation is dropping to absolute zero.
It really is something to think about the next time you stare at a blank code editor. Thank you so much for joining us on this deep dive.
It's been great.
Catch you on the next one.